Hello and welcome. Today we are going to solve the last problem in the series of 8 problems of JEE Advanced 2020 Paper 1. Today is the day for a problem on limits. E denotes the base of a natural logarithm and we need to find the value of the real number a for which the limit extending to 0 plus 1 minus x whole power 1 by x minus e inverse upon x power a is equal to a non-zero real number. Before starting the solution, let me digress a bit to give a brief introduction of E, the Euler constant. After pi, probably E is the most popular mathematical constant and there are many similarities between the two. Both are irrational numbers, not just irrational, both are transcendental as well. It means there is no non-zero polynomial with rational coefficients whose roots are E or pi. Indeed, proving these facts are not easy and this is beyond the scope of this video. Unlike pi, E has no simple geometric definition. There are many ways to define pi, perhaps these two are the most popular and commonly used ways. Of course, both are equivalent, but again, the proof is beyond from 10 plus 2 level. The first definition can be generalized to give e power alpha, and for alpha is equal to -1, we get limit x tending to 0 plus 1 minus x whole power 1 by x is equal to E inverse. That's it with the introduction of E. Let's start the solution. It is immediately clear that the limit is in 0 by 0 indeterminate form. We need to find the value of a in order to make sure the limit is non-zero real number. The trouble is that it is not immediately clear how to evaluate this limit. What standard limits do we have which might be helpful here? In terms of E, we have a standard limit x tending to 0 e power x minus 1 upon x is equal to 1, which is nothing but the paraphrase of the fact that the derivative of e power x at x is equal to 0 is 1. But how is this limit helpful here? Recall that ln x is defined as the inverse of e power x. It means we have e power ln x is equal to x for all positive x. Let the required limit be L and we can rewrite it e power 1 by x into ln 1 minus x minus e inverse upon x power a, which can be further simplified. We have another standard limit x tending to 0 ln 1 minus x upon x is equal to -1. Again, which is nothing but the paraphrase of the fact that the derivative of ln 1 minus x at x is equal to 0 is -1. We can manipulate L by using these two standard limits and we get L is equal to E into limit x tending to 0 ln 1 minus x plus x upon x power a plus 1. In order to evaluate this limit further, we can use the Taylor's series expansion of ln 1 minus x. By using the expansion, we are able to find the value of a if L is non-zero. Notice that this limit is non-zero real number if and only if the denominator is x square. Equivalently, a plus 1 is equal to 2, which gives a is equal to 1, and this completes the solution. We explained the solution in greater detail. This might give an impression that the problem was laborious, but it is not the case. The most difficult part of the problem is the starting point where we expressed 1 minus x whole power 1 by x in terms of exponential function and logarithmic function. After that, we followed some routine steps by using couple of standard limits. And then we concluded the problem by using Taylor's series expansion of ln 1 minus x. Instead of the expansion, we could use the L'Hopital rule that could hardly make a difference in terms of the length of the solution. Overall, this was a good problem on limits. That's it in this video. As you know that it was the last problem on the series of 8 problems of JEE Advanced 2020 Paper 1. Finally, we complete this series today. Hopefully this series was helpful for you and you enjoyed it as well. Don't forget to share your experience with us in the comment section. Soon we shall come with another exciting math video. In case you want a video on some particular topic, please let us know in the comment section. Thanks for staying with us till now. You might be interested in our amazing books. Check out the links in the description. See you next time.